Hi, this is Alex from devstories.eu, Async.io, episode 12 of 20. You're sending data over a network connection and your loop looks perfectly fine, but behind the scenes, your application is silently eating up gigabytes of memory until the system kills it. The issue usually comes down to one missing line of code that handles flow control. That is why we are looking at high-level networking with streams today. Async.io provides a high-level API to work with network connections without touching raw sockets or low-level transport protocols. To establish a TCP connection, you use a top-level function called openConnection. You pass it a host string and a port integer. It immediately returns a tuple of two objects, a StreamReader and a StreamWriter. If you're building a server instead of a client, you use startServer. You provide a callback function, a host, and a port. Every time a new client connects, Async.io triggers your callback, passing it a dedicated reader and writer for that specific client connection. The StreamReader is your interface for receiving data. It provides asynchronous methods to pull bytes off the network. You can read a specific maximum number of bytes using the read method. If you are parsing line-based protocols, you can read until a specific separator like a new line using the read until method. If your protocol requires a fixed size header, you can use read exactly, which will wait until that exact number of bytes arrives. Because all these operations depend on network traffic and latency, they pause your coroutine, meaning you must await them. Now the second piece of this is the StreamWriter. This object handles sending data back out. You use the write method to push bytes into the stream. Here's the key insight. The write method is a regular function, not an asynchronous one. You do not await it. When you call write, you're not instantly putting data on the network wire. You're simply putting data into an internal Async.io buffer. The underlying event loop tries to flush this buffer to the network in the background. This buffer is where developers run into trouble. Think about a TCP client sending a massive file payload to a slow server. If you put your write call in a tight loop reading chunks from a local disk, Python will read the file vastly faster than the network can transmit it. Because write does not block your code, your loop keeps spinning. The internal buffer absorbs the entire file, consuming all available system memory. This is where back pressure comes in. To manage flow control, you must pair your write calls with the drain method. The drain method is asynchronous, meaning you await it. When you await drain, you tell the event loop to pause your coroutine if the internal buffer has exceeded its high watermark. Your code waits until the background process pushes enough data over the network to shrink the buffer down to a safe size. The network gets time to catch up, the buffer clears out, and your memory usage stays flat. When you're finished sending your file, you call the close method on the writer. Just like write, close is not an async function. To ensure the connection actually shuts down cleanly and all final bytes are flushed before your program moves on, you follow it by awaiting the wait-closed method. The StreamWriter makes writing to a network feel instantaneous, but physics still applies. Always await drain after you write to ensure your application respects the actual speed of the network connection. Thanks for listening. Happy coding, everyone.